Hello everyone! Welcome to lesson number 3, partial sums of Unit 7. Partial sums is actually pretty cool, but we've got a do now that you need to do, and I want you to do it right now. It says to add all the numbers, all the whole numbers from 1 to 100. Why don't you go ahead and pause the video? No, I'm just kidding. Don't do that. That would be an incredible waste of time. I'm going to show you how to do that. I'm just kidding. Don't do that yourself. So here's the deal. The reason why I'm putting it here and the reason why I mention that it's an incredible waste of time is because there's a story of this mathematician, Carl Gauss. Now, I might be slightly wrong about this story, but this is what I remember hearing. Carl Gauss was in young lad school at one point, and he was kind of a troublemaking, super smart kid. And his teachers were very frustrated with him one day, and they told him, Carl, I want you to add all the numbers from 1 to 100. Now, he was very young, so they figured that this would have taken the kid a couple of minutes, that they could have went and done whatever they needed to do while this troublemaker was busy adding numbers. But young Carl, being a very brilliant young boy, figured out how to add those numbers very quickly. So quick, in fact, that the people who told him to do it, his instructors, they didn't know what the answer was at the time to their question, and it actually took them longer to figure out that he was correct, and they didn't believe him when he explained his method of doing it either. But now people definitely believe it, because we have a formula for this too. So you don't have to do this do now. This is just a joke. I don't usually do nows anyways. But here we go. It's called partial sum. Okay, the partial sum, the sum of the first n terms of a series. Now you might have noticed that we went from the word sequence to series, and that mostly has to do with what you're doing to the numbers. Right? A sequence is just a list, where a series, generally speaking, we're going to be adding those numbers together. So partial sum is when we're adding the first so many terms of a series, and we abbreviate that with S sub n. And here you have the arithmetic partial sum formula. This is the formula that young Carl Gauss, as a little kid, troublemaker, he had figured out that formula. What it says is, if you want to know whatever particular number, total number of numbers added together, so like the first 10 numbers, for example, or the first 100 numbers, right? That'd be the number that you're looking for. You're going to use that same n value. You're going to have your first value plus your last value divided by 2. And this is exactly what young Carl Gauss had said, right? If we have to add all the numbers from 1 to 100, he had said, well, what if I was to take 1 and add it to 99? That's 100, right? And if I take 2 and add it to 98, that's also 100. And if I take 3 and add it to 97, that's also 100. So he knew if I take the first number and add it to the last number, if I keep on doing that with the next numbers in sequence, closing their way in, obviously, then you're always going to get the same number right here. But because I'm using 2 numbers to get that, I'm going to have to divide it by 2 and then multiply by however many numbers I'm looking for. So it all really made sense to him, and it turns out that it works. So let's figure out what Carl Gauss got. Right? So from 1 to 100, that's 100 numbers. So he wants to know the 100th number. Well, there are 100 numbers that we're looking for. The first number would be 1. The last number would be 100 divided by 2. Now I can add these two up and divide by 2, no problem. But I can also take care of some of these other numbers, because 100 plus 1 is going to be an odd number, not divisible, so I can actually do a little bit of easier division out here. $50 times 101 is 5,000. Oops. And 50. So that's the number that you got when you add it up from 1 to 100. Supposedly. So let's check out a different problem here. Right, this time they give us some numbers that are starting randomly, right? 84 plus 90 plus so many numbers all the way up to 198. Now we have a kind of a big problem, because I don't know where that number is, right? I know this is the first number, I know that's the second, but I don't know how many numbers are in between here. That's not the third. It could be the fifth, it could be the ninth, it could be the 20th, I don't know. So we're gonna have to figure that out. The good news is we have some formulas that we worked with in the past that will help us solve that, right? I know that that is my nth term. And I know that 84 is my first term. The thing I don't know is I don't know what number that is. So I know it's going to be n minus 1. Remember, we're using the same formula from yesterday's work. The only thing I'm missing here would be the common difference. That's easy enough to find because I can do 90 minus 84, and that gives us a common difference of 6. What I need to do is solve for n. So let's see, 84, we're going to distribute just like usual, 6n minus 6. Let's see, 84 minus 6 is 78. Start solving by subtracting 78 on both sides. 198 minus 78 is 120. Then divide by 6. So it happens to be the 20th term in that series. But that's not even the question that they're asking. They want to know what is the total sum of all these numbers from 84 to 198. But in order for me to do that, according to this formula, I needed to know what n was. Now the good news is I already knew what a1 and an are because I gave those to us. So when we start doing the rest of this, right, I know that my n value is 20. I know my A1 value is 84. I know my last value is 198. And I'm going to divide by 2. Because what I'm doing is I'm adding these two numbers together. Then I'm going to add these two numbers, then these two numbers. And because I need 2 of each to make those, I'm going to divide by 2. And then finally, this is the number of terms I'm working with. So I would have to multiply by that 20. Now look, this is nice, right? I can reduce 10 times, let's see, 84 plus 198 is 282 times 10 gives us 2,820. Pretty cool stuff. I like it. I've always found it to be pretty fun. All right, I'm gonna go over one more with you before I give you one to try out. Okay, so if that went a little quick for you, here's what we have to do. In order to use the formula, it calls for n. We don't know n, but we do have a formula from last time that has n in it, our arithmetic means formula. So this is a1, this is an, and we know our an value, 153, is going to be equal to our a1 value plus n minus 1 times the common difference. We got to figure out the common difference. All right, no big deal. 13 minus 3 is 10. So here's our common difference. So this is the formula from yesterday. We need it to find n, and then we can plug it into the new formula from today. So we have to distribute. Combine like terms. And then solve. So it turns out that this is the 16th term in this series. What we want to know is, what does this all add up to? So our n value 16 times a1 plus an divided by 2. Again, I can simplify some of this stuff pretty quickly. right? That becomes an 8. So 8 times 156 is 1,248. Both formulas pretty easy to use. You know how to solve for variables at this point. Once you solve it, you plug it into a new formula. New formula is also pretty easy to use. So you've got one right here to try out. Pause the video and resume when you're ready to check. All right, let's check this one out. Here's A1. Here's AN. We need to figure out what that AN is. And let's find our D value real quick. 40 minus 25 is 15. So we have a D value of 15. So 220 equals 25 plus n minus 1 times 15, our common difference. Distribute this in. So plus 15n minus 15. Combining like terms leaves us with just 10. Now we can start to solve. So 210 equals 15n divided by 15. I got 14. So that tells me that this is the 14th term in this overall series. We want to know the sum of those first 14. So 14 times 25 plus 220 divided by 2. And I can get rid of that 2. That becomes 7. 25 plus 220 would be 245. $1,715. Not bad. Pretty easy. Now we're going to look at something else that's actually not bad and pretty easy. It's called sigma notation. And the cool thing about this is the way that it's written. Right? People really like the way that sigma notation is written, or some people don't, I guess, but I like it because it looks really fancy. It makes people look like, or it makes people who's looking at your work think that you're doing something super duper difficult. But in reality, it's really not that bad. It's just a different way of writing what we just saw, right? Instead of writing out some numbers plus some more numbers and stuff, this is written in a slightly different way. Sigma notation. So this giant capital E looking 3 thing here, this is called capital sigma. That's why it's called sigma notation. So you have this, it's kind of like an operation almost, and it's giving you some instructions. The number on the bottom, it's going to say k equals some number. It could be any number. A lot of times we'll start with 1, but maybe they want you to start at like the 8th number in the series. Okay, so depending on where you want to start, this is where we're going to start from. This is where we're going to stop. So this number is always going to be larger than the bottom number. So I might want to go from 1 to 18. Maybe I want to go from 5 to 22, right? But it's telling you where to start, where to stop. And then finally, this is the function of k that we're going to be adding. Therefore, it's a series. So what's going to happen is we're going to plug in this first number of k. Then we're going to plug in the second number of k and the third, all the way up till the last number of k. And whatever results we get, we're going to add along the way. And that's what this is telling us to do. So let's check out an example. Here we have k equals 1, and we're going up to k equals 15. So what would this look like? Well, if we were to do this full thing out, which we're not going to do the full thing out, we're only going to do a couple. But if we were to do this full thing out, it's telling us that we need to do 3 times 1 minus 1. That would be our first term. Plus, now we have to go up to the next one, so we would have to do 2. 3 times 2 minus 1. Plus, then we would go up to the next one, 3. 3 times 3 minus 1. But now, I don't want to do all 15 of those. That sounds like an incredible amount of work. So I'm going to skip a whole bunch, and I'm going to go right up to the last one. 3 times 15 minus 1. So what is this kind of starting to look like to you? It's kind of starting to look like what we had up here, right, where the numbers written down, but they're not written down the same way anymore. We've got to figure out what those numbers are. Okay, well, let's see. 3 times 1 is 3, minus 1 is 2. 3 times 2 is 6, minus 1 is 5. 3 times 3 is 9, minus 1 is 8. And then finally, let's see, 3 times 15 is 45, minus 1 is 44. So now it's starting to look more like what we've been working with earlier. And we can do the same stuff as earlier too, right? We'll find our common difference, which, by the way, that number right there kind of matches, right? No coincidence. And let's see. We know that this is the last term. So we're going to do 15 minus 1, our first term, but then we're going to also add 1 because, again, this is not always necessarily our first term. So we have 15 terms in this overall series. And now we can plug it in. We know exactly what we need. All right, so let's see. The sequence is going to equal 15 times our first number, 2, plus our final number, 44, divided by 2. I can't do that fancy trick with the 15 and the 2 here, so I'm going to add these up first. 2 plus 44 is 46. 46 divided by 2 is 23. 15 times 23 is 345. So if we were to add all these numbers, or if you were to do what this tells you, you would come up with 345. So quick recap. I'm not going to take too long, but quick recap, right? We figured out what our first term and what our second term, and we didn't have to even do the third. We only needed like a couple of these, but we definitely needed the last. We didn't have to find the common difference, but I was pointing out to you that that common difference was your multiplier. You should kind of be aware of that from linear functions at this point, right? It's just a constant growth that we have. But this is what we really needed. We needed what number term we were on. We needed to know what our first term and what our last terms were. So we just plugged in first term, plugged in last term, and figured out how many we had total. And then we were able to get the sum pretty quickly. So I'm going to do another one with you before I give you one to try out on your own. By the way, this is the last page for this lesson. So we're almost done. So we're going to find our first term. K equals 1. So we're going to do 2 times 1 plus 5. I don't care about any of the other terms except for the last one. 2 times 11 plus 5. So this is our A1 term. This is our AN term. So 2 times 1 is 2, plus 5 is 7. 2 times 11 is 22, plus 5 is 27. The number of terms that we have, if I start with 11, and I get rid of where we start, the 1, but because this is also the first one that we have, we would have to reintroduce that back in. We end up with 11 terms, right? If you were to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, that's 11 different numbers we used. Okay, this little trick with the 1 minus and plus thing, that's going to come in when we start looking at some further down problems. Anyways, if we want to know the total number, we want 11 times 7 plus 27 divided by 2. That's not divisible, so I'll have to add these first. 34 divided by 2 is 17. 11 times 17 is 187, I think. Oops. Yeah, 187. Ooh, I went a little too far down on that one. You have one to try out right here. Pause the video and resume it when you're ready to check. Just this one right here. Alright, let's see. You wanted to find your first term, so you would have done 5 times 1, because that's where you would start, minus 4. You would have went all the way up to the 8th term, so 5 times 8 minus 4. 5 times 1, 5 minus 4 is 1. 5 times 8 is 40, minus 4 is 36. Alright. The number of terms, we have 8 minus our first number, and then we're going to have to add the very first number back in. Those end up giving us n equals 8. Now we can find the solution here. I'm going to do it off to the side. So s, or the sum of all 8, we would want 8 times 1 plus 36 over 2. I can reduce the 8 over 2 right now. So let's see. 1 plus 36 is 37. 4 times 37 is 148. Hope you came up with that one. And like I said, this looks super fancy. If you show people at home, they're gonna be like, whoa, you're a mega genius. And you can feel proud because this is some advanced math that you're looking at here. So we got a couple more for us, and then we'll be done. I think we'll be done before the 30-minute mark. Let's hope. So this time, basically the same thing, but look where we're starting. We're starting at k equals 4. So when we do this, instead of plugging in 1, I'm plugging in 4 for my first term. Now again, I don't care about the middle terms, but I do want to know what is my last term going to give me. Alright, so 8 times 4 minus 11 is 21 for our first term. 8 times 14 minus 11 is 101 for our last term. So those are the two terms that we really need. We need the number of terms. Now this is where it kind of gets weird. If I take 14 and I subtract 4, that's great, but I'm going to have to add in that original term back in, right? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 is 11, right? But if I do 14 minus 4, that gives me 10. So where am I missing one? I'm missing the first one that I counted. Right, it's that whole n minus 1 thing, but this time, because we're doing it inverse, it'd be plus. So 14 minus 4 plus 1, that's 11 terms, and we just counted it. So we knew that that was the case. So here we go. If I want the first 11, we're going to do 11 times 21 plus 101 divided by 2. That won't reduce. 21 plus 101 is 122. That will reduce. All right. Times 11 is going to be 671. Okay, so I got one more to go over with you before I let you try your own. Very similar to what we just saw, right? So if you want to keep these in view as a reference, right? This is what we started with. We started by plugging in our first value. Then we plugged in our last value. We calculated what those were. 2 times 19 plus 4 would be 42 for our first term. 2 times 28 plus 4 is 60 for our last term. So we're adding 42 all the way up to 60. We want to know the number of terms between 19 and 28. So n equals 28 minus 19, but I've got to reintroduce that number, so I'm going to add 1. 28 minus 19 plus 1 is 10. Now I have everything I need, right? I have my n, my last term, my first term. So the sum of those 10 is going to be 10 times 42 plus 60 divided by 2. Simplify some stuff along the way. 42 plus 60 is 102. 2 times 5 is 510. Okay, so in both cases, we found our first, we found our last, we figured out the number of elements we're working with, which was that whole subtract and add 1. And then we plugged into the summation formula. So you got one more to go. I bet you we'll get out of here before the 30-minute mark. Pause the video and try this one out. Resume when you're ready to check. All right, let's see what you did here. You should have started with 4 times 6 minus 8. And then you should have found 4 times 17 minus 8. That would have been our starting point. 4 times 6 minus 8 is 16. 4 times 17 minus 8 is 60. Then we need to find our n value. 17 minus 6 plus 1 gives us 12. So these are all the numbers that we need for our summation formula. 12 will reduce to a 6. The 2 will go away. 16 plus 60 is 76. 6 times 76 is 456. Hopefully you got that number. So there you go. There's sigma notation and partial sums. So we started off this lesson talking about Carl Gauss being a naughty little kid in class, and his teacher's trying to punish him by adding up a whole bunch of numbers, but he got the last laugh because look what basically came up from his punishment is all of this math. So we got one more lesson in Unit 7, and I'll see you there. Bye.